we're going to look at normal distributions. This normal distribution chapter is a very important chapter. The concepts that we learn in here are going to come back in probably 3 to 4 other chapters after this. So make sure you understand this material by the time you get to your quiz and or your exam. We're going to start off with density curves. Density curves are just a distribution of your data. Density curves are always above the horizontal axis. Their area underneath the curve is always 100% or 1. So suppose we consider a histogram of 947 seventh graders. We would get these bars going up and down. If you draw in a smooth curve going over the top of your data, you would get this curve right here, which is basically a normal distribution curve. A bell-shaped curve like this is typically referred to as a normal distribution. Now, if you smooth out the top of these bars, you would end up getting this right here. So if you were looking for all the actual data that was less than a 6, that would be the heights of all these bars here. But if you smooth it out and you looked at the theoretical data that was less than a 6, that would be all the area underneath your smoothed out curve. Now, here we have a uniform distribution. Remember, in a uniform distribution, your mean and your median are always in the exact center. Whether it's a uniform or symmetrical, ends up being the same. However, keep in mind that when you're dealing with a skewed distribution, your mean is always pulled in the direction of the tail compared to your median. When you're dealing with these density curves, you're going to be coming across an X bar and an S, a mu, and a sigma. X bar and S are always the mean and standard deviation that you get from your sample or from your data. Whenever you're dealing with the whole population, you're dealing with a mu for your mean and a sigma for your standard deviation. Normal distribution is a bell-shaped curve. Typically, if you see an n within parentheses after it, the first number is going to be representing your mean. Your second number is going to be representing your standard deviation. Now, to be able to graph these, if you wanted to graph them, you would have to use this formula here. Not exactly something that's easy to do for most people, including me. Now, pi is the irrational number pi. It's a little bit more than 3. E here is the natural number e, which is about 2.7. And then you also have x minus your mean squared over your standard deviation. It's not one that we typically are going to go ahead and try to graph by hand. We will go ahead and do sketches of these. If you are sketching them, wherever your mean is of your population, which is mu, that's going to be the center of your distribution. The bigger your standard deviation, the farther it's going to go to the right and to the left, so therefore it's not going to be as high. The smaller your standard deviation, the narrower it's going to be, and so therefore the taller it has to be, because remember, your standard, or the area underneath your curve always has to add up to 1. So if you're not as wide, you got to be taller to get that same area. So here, let's take a look at some normal distribution. Here we have our mean being 15 right here in the center. But we have a distribution here, standard deviation for the blue being 2, where for the purple, it's a standard deviation of 6. When it's bigger, it's spread out a lot more and therefore has to be wider. Once again, when it's narrower, standard deviation is smaller, it has to be taller to find that whole area. If you go ahead and instead of keeping the or changing your standard deviation, you keep your standard deviation the same, but you just change your mean, all you do is you just take your curve and slide it to the right or slide it to the left, depending upon where it is. And once again, your mean has to be right where the peak is on a normal distribution or standard curve. Now, normal distribution curves share the same property, that if you go from your mean, and in this case we're calling our mean 0, if you go one standard deviation to the right, one standard deviation to the left, that's 68% of all your data. And by the way, at one standard deviation to the right and one standard deviation to the left, that would be here, and here, your curve switches from kind of curving down to then starting to have more of an upward curve. So keep that in mind. Now, if you're going two standard deviations to the right of your mean, two standard deviations to the left of your mean, in between the two standard deviations on each side is 95% of your data. If you happen to go three standard deviations on each side, you get 97% or 99.7% of your data. So you can always go ahead and look at your data in terms of standard deviations, how far you're above and below your mean. Here we have a normal distribution of 64.5 for your mean and 2.5 for your standard deviation. This happens to be the heights of women. It's normally distributed. That's what the n means. So if you go one standard deviation to the right and to the left of your mean, so 2.5 onto your mean, that's where the 67 comes, and 2.5, which is your standard deviation out below your mean, that's where the 62 comes from. One standard deviation on each side goes from 62 all the way up to 67. That's going to be 68% of your data. If you would add your 2.5 twice to this, 2.5 to get to here, another 2.5 to get to here, you'd be at a 69.5, or 2.5 subtracted and another 2.5 subtracted, that's 59.5. So from 59.5 all the way up to 69.5, that's two standard deviations above and below your mean. That's 95% of your data. Now, how many standard deviations above and below your mean you are ends up being your z-score. Z-scores just tell you how far above and below your mean you are. Now the 68, 95, 99.7 rule works great when you're 1, 2, or 3 standard deviations on each side of your mean. It's not the most exact, but it's really pretty close. If you want a more precise process, we'll be looking at that later. Now, suppose you have adult men, 18 to 24, their mean is 70 inches, standard deviation of 2.8 inches. It's normally distributed. If you're looking at the 68, 95, 99.7 rule, we would say 68% of the men are from 67.2 to 72.8 inches tall. Where do these numbers come from? Well, 68 is one standard deviation on each side of your mean. So you take your mean and add one standard deviation, and that's where the 72.8 comes from, or your mean minus your one standard deviation, that's where the 67.2 comes from. 95% you know is two standard deviations. So you got to take your mean and add and subtract two of those standard deviations. So 95% of all the men in that age range are from 64.4 to 75.6 inches tall. And then we also have 99.7, which is three standard deviations on each side. Now, some students like it when a teacher grades on a curve. Technically speaking, grading on a curve is using a standard normal curve. That's not what most people think of when they hear grading on a curve. Now, if you had a class of 20 students and you were technically grading on a curve, 14 students would get C's because you'd end up having 68% of your 20, which is about 13.6 people, but we can't have part of a person, so we round it to 14. 3 people would get B's, 3 people would get D's. Whether they really had percentages, your grade that you have in the grade book, really in the D range, would be a different story. But grading on a curve would say you have to have 3 people in the D range. Now, that means nobody would end up getting A's in a class of 20. The good news is that means nobody would fail in a class of 20. Now, as we're looking at this, we are looking for something from the sample. That ends up being x bar. X bar is the mean of your sample. Mu is the mean of your population. Sigma is the standard deviation of your population. P is the proportion of your population, and what we mean by that is when you're dealing with categorical data, like what percent of your population. Now, what's false about your standard normal distribution? Well, that your mean would be greater than your median. Remember that it's symmetrical and bell-shaped. It only has one peak, so therefore, since it's symmetrical, your mean and median have to be the same. Now, on here, we have our mean being 0, standard deviation being 3. Well, when we look at our standard deviation being 3, well, here's about 3, here's about negative 3, here's about negative 3, here's about 3. So showing up on your curve shows up here and here, or on your curve it would be about here and about here. We had said earlier that where your curve switches from going kind of like a parabola or a curve going down to part of a curve going and opening up is 1 standard deviation. In this graph over here on the left, that would occur about here. Definitely not where our marks of 3 are. Over here, our 1 standard deviation to the right and to the left occurs at these spots. So therefore, a mean of 0 and a standard deviation of 3 would be for this second graph. Here we have a mean of 8,000, standard deviation of 1,000. What percent of the games are between 7 to 9,000 people? Well, 7 is really 1 standard deviation below your mean. 9,000 is really 1 standard deviation above your mean. So 7,000 to 9,000 is really 1 standard deviation on each side. If you're 1 standard deviation on each side, then you know that that correlates to the 68% of your data. So what portion of men are less than the 72.8 inches tall? Well, 72.8, remember that our standard deviation was 2.8 and our mean was 70. So that's really this part right here, going 1 standard deviation on each side because 72.8 is 1 standard deviation above. But it also includes this area down here. We know 1 standard deviation on each side is 68. Keeping in mind then that the whole area, the 2 tails, the middle, has to add up to 1. Well, the 2 tails then end up being 32% of your data. Well, 32% of your data is for both tails. We only want 1 tail, so that means one of the tails would just be half of this. Half of 32 is 16. So that's where this 16 comes from. So we have our 68 here and our 16. We add those together and we get a total of then of 84. So 84% of our data is below there. Question is, what happens if you're at 68 inches tall? Remember that our standard deviation was 2.8. 68 is not a full standard deviation below. So what do we have to do? And we'll investigate that on the next slide.